So now we again start with, in the last class we have studied the Newton's laws, first and second laws of the motion, and we have found that the first law gives us the definition of the force, and second law gives, first law is also a statement of a reference frame, and second law gives us the measurement of the force, and it relates two unknown quantities, force and mass, which was till then unknown or undefined. Newton's related the two unknown quantities, force and mass, by one single equation, and that is F is equal to ma. Now today we are going to discuss about the third law, and then we will apply Newton's laws to various problems. So the statement of the Newton's third law is, to every action there is equal and opposite. There is equal and opposite reaction. So here, this law is very common, everyone knows, but how to apply it's something times it becomes difficult, nebulous, when we don't understand what is the action and what is the reaction. So here we have two quantities. One is action and another one is opposite reaction. So in order to apply Newton's laws of motion, the object or the system or the particle on which the Newton's laws is applied, or whose motion we want to study the motion of that particular particle, we call that particle or that as particular body as a system. So the object on which we focus our attention, that is called system. That we call as system. And all other bodies around the system will be called surroundings. So we have two set of things. One is the system and another is surrounding. So the system is that physical object or that physical body on which whose motion we want to study. That we call as system, and all others are surroundings. So if the system, the surroundings, they may interact. System may interact with the surroundings and surrounding may interact with the system. If the system applies certain force on the surrounding, and if that is called action, then the surroundings will also reciprocate with the same force on the system, and that will be called the reaction. We will do this by applying. Suppose, this will you understand when we apply it. Suppose we have an apple. Suppose there is an apple, and we want the motion of this apple only. So this is our system, and all other objects around it, including us, is the surroundings. The air around us, everyone here sitting in this room, the earth, and everything outside the apple, surrounding the apple, is called the surroundings. Now the action on the apple may be due to the air pressure. Air is also from the surrounding. This is not a system, and this is our system. Here, apple is our system, and the air, the earth is also from the surrounding. Air may apply pressure from this side, this side, this side. If we ignore for the present case, or to make easier problem, we just let the pressure, we ignore the pressure, air pressures, because the pressure from this side will apply on the system, that is apple. The apple will apply the same force here, so, and similarly both the pressure from this side will transfer. So at present I am ignoring the air pressure and all other objects. Suppose it is only earth and apple is here. So this is, if this is system, the earth is its surroundings. Now the action and reaction will be in between these two. Now suppose the earth applies a force on the apple or the system, that is earth attracts the apple by certain force, say F. Then what will apple do? The reaction will be on the surroundings. If the action is on the system, the reaction will be on the surrounding, and surrounding is here earth. It means the apple is also pulling the earth by the same force F. If this one is F1 and this is F2, Newton's third law, according to this third law, these two must be same. Is here action is force of attraction on the apple by the earth. Force of attraction on the apple by the earth. Let it call as F1. Then the reaction will be the apple will attract the earth. So apple attracts the force and the earth by the force, say F2. According to third law, these two must be the same. So F1 is equal to the force by which the earth attracts the apple. By the same force, the earth will be attracted towards the apple. So this is the meaning of action and reaction. The action is on the system, the system is also applying on the surroundings. So if this force acts on this apple, what will this force, according to Newton's second law, will give? It will produce a change in the inertia of the apple. It means that it will produce an acceleration in the apple, and that will be written as F1 is equal to ma, where m is the mass of the apple and a is the acceleration of the apple. And F2, suppose we call it as FA. Now F2, force on the earth, is equal to mass of the earth. This force will produce an acceleration of the earth towards M. But these two forces must be same. So here F1 will be F2 according to Newton's laws of motion. These two are equal and opposite, which means MA1 is equal to ma2. But since the mass of the earth is very large, infinitesimally large as compared to the mass of the apple, so its acceleration, consequently its acceleration will be infinitesimally small. So since m is very much greater than m, a2 is very much less than a. So if the acceleration of apple is more prominent than the acceleration of the earth. That's why we see that all this also, since we are sitting on the earth, that's why we don't see our acceleration. We think that apple is falling down. If we sit on the apple, we will see, it will appear that the earth is moving upward. So this can also be understood when we study the center of mass. Then this will be more clear. Here is for the action and reaction. So I will apply some more examples. We will do just some more examples. Let us have a block. And suppose this is this is a string or rope, whatever you call it, a rope. This is a block. Now suppose that external force is applied here. So we have here two separate objects. One is rope and one is block. So in order to apply Newton's law, we isolate. Suppose the rope is isolated. Now here our rope acts as a system, and the surroundings here will be the external agency which applies force here, and the block is also external to this. And we assume it's a motion only along horizontal, so we are not discussing the effect of gravity here. And suppose that there is no friction, it's moving on a frictionless table. So the reaction, if this is our system, rope is our system, the surroundings is the block and the agent which applies the force. These two are surroundings. If this surrounding acts force here, this block will apply a force F1, because since it's attached, the intermolecular force between the rope and the block this block will not will apply certain force. So according to Newton's second law of motion, the resultant force must produce an acceleration. So the resultant force here is F minus F1 is equal to mass of the rope and acceleration of the rope. So the equation for this is already written. Now this has been done. Now this block. Now for this block, for the block capital M, this rope acts as a surrounding, because this is our system. We are concentrating on this block only. So this rope acts as a surrounding, and this surroundings, let this surrounding acts on this block, certain force, say F2, and there is no another surroundings here which may apply such force. So this F2, according to Newton's law, will produce an acceleration. So this will. Now what Newton's third law says, that this, if this is the action by this block on the rope, so this will be the reaction by the rope on the block. So F1 is action by the block on the rope. Then F2 is the reaction of the block by the rope. Now since F2, 1 and 2 must be same, according to third law, so these two will be same, and hence we can solve this problem. Simply do what we do, simply add these two cancels out, and this will come out to be F is equal to M plus M as, and the acceleration can be calculated out from this. Now suppose, now take one more example. Yes, example. Now suppose we have two blocks connected by a rope of mass M. And suppose the table is frictionless, no force acts between the table and the block, and if this one is having mass M1, this one is having mass M2, and this rope having mass M. Now suppose the external agent here applies a force F, and I am considering, or we are concentrating on the motion of this block only. So this is our system, and all other are surroundings. So this will be M1. F is the surroundings, apply a force F here, and this rope which is attached to the block applies, say, force F1. So according to Newton's second law, the equation of motion for this will be F minus F1 is equal to M1A. Now we have the rope as our system. Having mass M. Now if this is the action on the rope, the reaction by the block on the rope will be F2. Now this rope is also attached to certain block here, M2 block. So that M2 will act as surroundings on this rope, and this will apply force here, F3. So the equation for motion of the rope is F2 minus F3 is equal to mass into acceleration. Now if F3 was the action on this rope, the reaction of the rope on the mass M2 will be, say, this is, say, F4. So this F4, there is no other thing surroundings, only F4 is the surrounding force or external force. So F4 is equal to M2. Here the accelerations of all of them are same because they are attached, they move to the same acceleration. Now according to Newton's third law, F1 and F2 must be same because they form a pair of action and reaction. And F3, F4 also same. They form a pair of action and reaction. So if this and this are same and these two are same, if you add, this will cancel with this will cancel with this, and we'll get the result will be equal to F times M1 plus M plus M2, okay, or A as F by M1 plus M plus M2. If you take the numerical, suppose the mass are given, suppose this is 5 kilogram mass, rope is 1 kilogram, and this is 4 kilogram. Let M1 is 5 kilogram. Mass of the rope is 1 kilogram, and mass of the second block is say 4 kilogram, and the applied force is say 40 Newton. So the acceleration of the system will be 40 by 5 plus 1 plus 4, that is 4 meter per second square. The whole system will move 4 meter per second square. And if you want to find the force on say particular blocks, say we want to find the force on M1 only, so the resultant force on the M1 will be, the resultant force on the M1 is F minus F1, that is equal to M1A. So that means the force on M1 is equal to force on M1 M1, and M1 is 5, and that is 4, so it is 20 Newton. Now if you want to find the force on the rope, so the force on the rope is this much, F2 minus F2, which is equal to MA. So this is the force on the rope, which is equal to MA. The force on the rope, force on the rope is equal to MA. M is 1 kilogram and this is 4 kilogram, so it is 4 Newton. And now the force on this M2 block, the force on the block M2, which is equal to M2A. So this is M2 times A, and M2 here we have taken as 4, acceleration we have calculated as 4, so it is 16. Now you have seen, yes, that the external force was 40 Newton. We have 40 Newton, and to produce an acceleration of the system by 4 meter per second square, this 40 Newton is divided among the ropes and blocks according to their masses. The inertia of this is more, so this requires more force. The inertia of this is very small, so it requires lesser force. So this, out of 40, this has kept itself for 20 Newton is kept here for its, and the remaining 20 Newton is here, applied here. So if you want to find action and reaction between M1 and the rope, which is F2 and F1. So if you can calculate F1 or F2 also. Either you calculate F1 or F2, result will be the same. So if you calculate F1, F1 is F minus, F was 40 Newton 40 Newton was applied here. This has kept for itself to change its inertia by 4 meter per second square. This requires 20 Newton, which is A40. So this has supplied 20 Newton here. So here 20 Newton is applied between these two. Now out of the 20 Newton, 4 Newton is reserved for this rope, and the remaining 60 Newton is transmitted to this. So you have seen that how this 40 Newton has been divided. The bigger the mass, it has taken the larger force has taken, because they have to accelerate with the same acceleration. They divide the force according to their inertia or according to their masses. So now one more problem. Suppose we have 3 blocks. Now we will do some faster, because now we have understood how to apply. I will do this one a bit faster. So we have M1, M2, M3. Ropes are M1, M2. Now you can do by using, not by drawing anything, just you can write that suppose F force is here. You can say that F minus says F1 is acting between this rope and M1 and small m1 and M. So we will write F minus F1 is equal to M1 here. Minus. Now this rope here, this applies force F1. So this block will also apply certain force, say is F2. So F2 here, and this is not free, it is attached to M2. So this will here the block will pull it by say F3, and its mass is M. So we can write F2 minus F3 as MA. Now if you have 3 this block M2, this is F3 is applied by the M2 on the rope. The rope will also apply with the same certain force, that is called say F4. And here is say F5. So it will be F4 minus F5 is equal to M2A. Now this F5 here, F4 minus F5, F6 will be, suppose this is the rope here again, M2, this is say F6, and this is, let's say, F7. So F6 minus F7 is equal to M2A, and the last block M3, say F8. So it is F8 is equal to M3. Now here F1 and F2 are action and reaction here. Here action and reaction are F3, F4. F3, F4, and here F4, then it is F5, and here's F6 on the rope, and here's F7 on the rope, F8 on the block. Now here we have seen that F1, F2 are the reaction. Here F3, F4 are the action reaction. So according to Newton's law, F1, F2 must be same. So F1 must be equal to F2. F3 must be equal to F4. F5 must be equal to F6. And F7 must be equal to. So if you substitute these values and add all these equations. So now we have 5 particles on which we are concentrating we are taking the equation of motion of, we have 5 objects, so there must be 5 equations. So it is 1, 2, 3, 4, 5. 5 objects which are in motion, and the equation of motion for each of them is written here. Now, if F1, F2 are same, if all add this, F1, F2 will cancel out, F3, F4 cancels out, F5, F6 cancels out, F7, F8 cancels out, and you are left with, on the left hand side, this is only F, on the right hand side, sum of these. So M1 plus M plus M2 plus M2, small m1, small m2, m3. So this is capital M1, small m1, capital M2, small m2 plus capital M3 times acceleration. Our acceleration is given by F by M1 plus M1 plus M2 plus M3 plus M1 plus M2, oh, it's M2, it's M2. Now if you put the numerical values, suppose the masses are, let the masses are, consider the masses to be, let M1 is 6 kilogram, M2 is 5 kilogram, M3 is 4 kilogram, M1 is equal to both the ropes are supposed taking of equal masses, but of 1 kilogram both. And let the applied force is 68 Newton. So acceleration will be, obviously acceleration 68 divided by 17, that will be 68 divided by 6 plus 5 plus 4 plus 1 plus 1, 6, 5 plus 4 plus 1 plus 1, that is 68 by 17, that is equal to 4 meter. Okay, meter per second. Now if we take the mass of the rope to be 0, suppose the ropes are massless. Now if we assume let the mass of the rope or if you take mass of the rope as are negligible, or if you take massless ropes. Okay. Ropes are massless. Ropes are massless. Consider it's not true that there must be certain mass, but for convenience, suppose we have taken masses of the rope as 0. Ropes are massless. Then what will happen here in this equation? If the ropes are massless, it means M1 is equal to M2 is equal to 0. And now this the equation will change a bit. Suppose this is equation 1, this is equation 2, this is equation 3, this is 4, and this is 5. Now, if this is 0, it means F2 is equal to minus F3 is equal to 0. So equation 1 will remain as it is. F minus F1 is M1A. And equation 2 becomes F2 minus F3 is equal to 0. And here F4 minus F5 is equal to M2A. And this one is F6 minus F7 is 0. F8 is M3A. Now, if F2 minus F3 is equal to 0, this means, this implies that F2 is equal to F3. And here this implies that F6 is equal to F7. So our situation becomes like this, that F1, F2 were action and reaction, F3, F4 were action and reaction, but F2 is equal to F3. This F2 is equal to F3, which means F1, F2, F3, F4, all of them are equal. Okay, so here the situation becomes like this. F1 is equal to F2, which we have already discussed. Now in this case, ropes are massless. F3 and F4 were equal, but F2 is equal to F3 and F3 is equal to F4. Okay. Now here, F5 and F6 were action-reaction, these two were action-reaction, but F6 is equal to F7 because of ropes being massless. F6 is equal to 7. So 5 is equal to 6, 6 is equal to 7 is equal to 8. So it is F6, 5 is equal to F6 is equal to F7 is equal to F8. Let us denote by one simple letter called as T1 and this as T2. Now the situation becomes, the picture becomes like this. This becomes, that it is M1, M2, M3. This has no mass, this has no mass. So it means our equation becomes, and this means that if there is no mass, the string acts as an agent which transfers the force from this block to this block without using, because it has no mass, no inertia. It will not keep some of the force for itself. It will just simply transfer from here. So that's why this force which is here is being transferred to this. F1 is equal to F2 and F2 is transferred to F3. The whole force. So here, if this is say T1, so it is, and suppose F1 is this T1 is equal to F1, F2, F3, F4. Both are same. Here also same, there also same. So it is here. So if the ropes are massless, if the connecting strings are supposed are taken as massless, this simply acts as an agent. Acts as an agent which transfers force from one block to another without any loss. Without any so now this is mass resistance. So we have only two particles, and the equation of motion will now then be only three equations will remain. So okay, I'm writing this one. So the equation of motion will be F minus T1 is equal to M1A. Now the story of this goes on, because this is the action, this is the reaction. So the resultant force on this is F minus T1. Now the resultant force on this will be T1 minus T2. So it will be T1 minus T2. And the resultant force on the third block is only simply T2. So it is T2 times now solve the adds, so it cancels out, and you get F is equal to M1 plus M2 plus M3. Okay, and there will then be F by M1 plus M2 plus M3. Now putting the numerical values which we have already taken, 68 Newton here, 5, 4, 6, 5, 4, 6 plus 5, so it is 68 pi by 15, 4 point something, so 8. This will goes on, so this acceleration here is 4.41 and so on. So all about this, there we will apply certain more cases we will take in the next class. We will go further, and so for today's I am leaving it here after this problem. You can try yourself from the books, some problems. Okay.